Alrighty, hello there. We're here to present to you Rust's Biosemantics. I am John Odom.
I'm Peter Delavorius.
And I'm Kristen Hanslick.
Okay, so Rust is a safe systems programming language. And what we mean by that, it's kind of like a safer version of C++ almost, where there's a bunch of different safeties that are in place in order to prevent seg faults, memory leaks, and thread safety. But here we're meant to talk about the borrow checker.
Here's an example of some C code that creates the dangling pointer problem. This aliasing of x, aka having a second pointer to some memory on the heap, is not allowed, and instead y must borrow the value from x, which ensures that x cannot delete memory while y is still pointing to it. Here's the same functionality implemented in Rust as we saw implemented in C on the previous slide. Unlike with the C code, an error will be thrown at compile time due to Rust Biosemantics and will not allow for the possibility of a dangling pointer. Here we can see another example of code that creates an undefined state that would be allowed in C but not in Rust. This particular race condition issue would not arise in Rust, as immutable x could not be used to call start twice, as functions in Rust borrow variables much in the same way as variables borrow other variables.
Here we can see the previous slide's shared mutable memory program implemented in Rust. However, in this case, Rust will not compile because we're trying to take two mutable references of x at the same time.
Borrowing can be thought of much in the same way as one friend letting another borrow their car. If y borrows x's car, then x cannot access his car while y is borrowing it. There are two ways to borrow variables in Rust: immutably, where the state of the variable cannot be changed by the borrower, and mutably, where the borrower can change the state of the variable.
So here are the borrow checker rules. The biggest one here, obviously, is a reference cannot outlive the memory it points to. Below that is a table that shows the valid inputs, particularly showing that you cannot have two mutables simultaneously.
In Rust, all variables and borrows have lifetimes, and that lifetime begins in initialization and ends with enclosing scope. Below can be seen the same code written twice. On the top is what the programmer would write, and on the bottom is how the compiler would interpret the scopes of each variable.
BarCK is a part of Rust's static type checking system, and it checks that a Rust program doesn't do any unsafe borrows. BarCK works in two passes: gather loans and check loans. Gather loans finds all the borrows in the abstract syntax tree and turns them into loans. Check loans checks that every expression in the generated LLVMIR doesn't violate any of the loan restrictions in scope at that point. Gather loans turns all the borrows in the AST into loans. A loan has all the things a borrow has: a borrowed location value, a lifetime, and a mutability qualifier, but it also has a restriction list. The restriction list contains all of the location value operations which are prohibited while a borrow is in scope. A restriction is a list of restricted actions and the location value they apply to. For example, R2 restricts assigning to y, i.e. mutating, taking mutable references of y, i.e. claiming, and taking immutable references of y, i.e. freezing. Before gather loans turns a borrow into a loan, it has to check that the borrow is legal. To do this, gather loans checks that the mutability and lifetime of the borrow are valid, and that the aliasability of the borrow is compatible with the aliasability of the location value. If any of these checks fail, then Rust will throw an error at compile time. To check if a borrow's mutability is legal, we look at the borrowed location value's mutability. If the location value is immutable, we only allow immutable borrows. If the location value is mutable, then we allow immutable or mutable borrows. Also note that this and the following inference rules apply only to local variables. Non-local variables have more complex rules. A borrow's lifetime is legal if and only if its lifetime is less than or equal to the lifetime of the borrowed location value. This rule prevents dangling pointer situations. A reference cannot outlive the memory it refers to. The aliasable rule says whether or not the reference created by a borrow is aliasable. A reference should only be aliasable when the reference is immutable. Mutable references should not be allowed to be aliased. This information is then compared with the aliasability of the borrow location value, and if the two are compatible, then the borrow is legal. The restrictions for a mutable local variable are mutate, claim, and freeze, but the restrictions for an immutable local variable do not include freeze. This is because we want to allow aliasing when the references are all immutable. Also, as stated before, this rule only applies to local location variables, not to reference location variables like pointers or field references. To generate the restrictions for a field location value, we must also include restrictions on prefix location values. This is because, for example, any mutation on the local value x may mutate the location value x.f. After gather loans is completed, check loans enforces the generated restrictions on a program by checking that each expression in a program does not violate any of the restrictions in scope at that point. If check loans passes, then your program is safe, as long as you didn't use the unsafe feature of Rust anywhere.
Our sources for the presentation include the official Rust GitHub repository documentation as well as the official Rust book. Both of these are shown here.